you put all this together, you apply your electrodes, and you can use an electrometer, which is used in physics. And in this example, if you have zinc and zinc 2 plus and a copper and copper 2 plus cell, and you add a wire between them and a salt bridge to connect them, you're going to measure 1.10 volts. So if you attach a wire to a zinc 2 plus electrochemical cell, and you connect it to a copper 2 plus cell with a salt bridge in between, and you hook up an electrometer, which is what you see in that middle part right there, you're going to read 1.10 volts. And 1.10 volts is the electromotive force, the EMF, of this cell. Positive E cell values are the ones that are spontaneous, the ones that happen. So if you get a positive E cell value, that means that the electrons are definitely going to start flowing in this. And it's really cool then to think about what's being oxidized and what's being reduced. So you can see up there in the picture that electrons are moving from the zinc to the copper. So what that means is that zinc is giving up electrons to become zinc 2 plus, and those electrons go from the zinc side to the copper side. Copper 2 plus is going to gain those electrons to become copper metal. And in the process then, the anions will move across the salt bridge to kind of keep the electrobalance going. It's a pretty cool kind of thing. And this is how scientists not only create usable current, but you can also predict then if a cell is going to happen or not, if it's going to be spontaneous or not. Remember, positive E cell values are the spontaneous ones. Those are the ones that are going to occur. So if you calculate a negative E cell, it probably won't happen, but positive E cells, those are going to just happen by themselves, no problem. To actually do some chemistry on it, to figure out the reactions that are happening, you want to balance those half reactions, add them together to give an overall balanced equation. Just remember that the oxidized part is going to have to be flipped when you look at that table of reduction potentials, because again, oxidized parts are not listed on the table, only reductions are. You can flip it though and see what happens. So as an example for this exact reaction, it's copper 2 plus and zinc going to zinc 2 plus and copper. If you look on the table, you'll see zinc 2 plus and 2 electrons going to zinc with a minus 0.763 volts. And you'll see copper 2 plus and 2 electrons making copper metal. E is positive 0.337 volts. Now we can't have, as is listed right here, we can't have two reductions. We have to have something being oxidized. And sure enough, if you look at that long enough, you can see that it's zinc going to zinc 2 plus, not zinc 2 plus going to zinc. So we're going to flip that reaction around. We're going to flip the zinc so that zinc's a reactant, makes zinc 2 plus and 2 electrons as products, and we're going to change the sign from negative 0.763 to positive 0.763. And now that looks a lot more like the reaction that we're actually seeing. You've still got copper 2 plus going to copper. We're not going to change that one, but we will flip the zinc one, and that's kind of the punchline here. So you flip the zinc, so it becomes positive 0.763. You add that to the 0.337, which you read directly from the table. And when all is said and done, you're going to end up with a cell potential of positive 1.100 volts. And that is exactly what you see as long as you're at 25 degrees Celsius and your solutions are all at 1 mole per liter, which is really, really cool. So this is how these cell potentials can be used to help chemists, all right? You can predict what the cell potentials are, and then you can actually record them in the lab. And most of the time, as long as the solutions are the same and the temperature is about the right, 25 degrees Celsius, you'll get excellent results, which is pretty cool. Here's a reaction. Nickel is reacting with the wild mercury 2 plus ion. It makes nickel 2 plus and 2 mercuries. Mercury is a liquid, by the way. It's one of the few liquids on the periodic table. Anyway, we want to find the cell potential for this reaction, and we're given these two reactions as listed. Now notice here that nickel is being listed as an oxidation. It's giving up 2 electrons. And the mercury 2 plus is listed as a reduction. reduction. So the mercury 2,2 plus, that positive 0.79 volts, we could find that from a table. But the nickel one, we would have to flip that around. It's probably listed at minus 0.25 volts on the table. Anyway, we're not worrying about that here. We want this reaction right here. And you can see if you just add these together, the 2 electrons, which are products, cancel the 2 electrons, which are reactants. You end up with nickel metal and the mercury 2,2 plus ion on the reactant side. And on the product side, you've got nickel 2 plus and 2 mercuries. To figure out the cell potential then, we literally just add those cell potentials together. 0.25 volts plus 0.79 volts. And that comes out to be 1.04 volts. So the cell potential for this reaction came from the half reaction cell potentials. We just added them together, in this case 1.04 volts. And again, notice that I already flipped the nickel for you. It probably wouldn't be listed as positive 0.25 volts. You'd probably see minus 0.25 volts. That would be for nickel 2 plus and 2 electrons making nickel when you want the opposite. So we'll come back to that here in a little bit. But the cell potential, 1.04 volts. The book likes using E cathode minus E anode, and I honestly don't like that system very well. What it's implying is that the anode here is going to be, for example, the nickel, all right? Because nickel here wants to lose electrons, not gain electrons. So you have to know which is anode, and I find that students find this confusing. So that's why what I would do is write your half reactions out as you want. So we want nickel going to nickel 2 plus. We're going to flip that nickel reaction around and change the sign. And if you change the sign there, you don't have to go cathode minus anode, all right? But you find the method that works for you. I really want you to try this. Make sure that you're getting the results I'm going to give you. And if you do, you've got it down. Just find the system that works for you, okay? And let me know if I can help. Another system that's used sometimes is what's called the northwest-southeast rule. I'm not really a big fan of this either, but here's the idea. If you have a table of reduction potentials, so everything's listed as a reduction, and all the cell potentials go from most positive to most negative, then what it means is you're going to get a product-favored reaction between the reducing agent in the southeast corner and the oxidizing agent in the northwest corner. Remember, reducing agent means oxidized. Oxidized is in the lower right, and then the oxidizing agent will be reduced in the upper left, the northwest corner, all right? So as we saw earlier, zinc and copper 2 plus will make copper and zinc 2 plus. This is an example of the northwest southeast, all right? You've got zinc and copper 2 plus, and as long as you use something up and to the left of your lower and to the right piece, you will have a product favored reaction. I find this a little confusing, and I don't know how helpful it is. I would once again just make sure everything was written oxidizing and reduced and add them together to figure out the cell. But again, I want you to hear all these different options because they are different ways to solve these problems. So what I would do, let's say we wanted to find the cell potential for this reaction right here. 2 aluminums and 3 nickel 2 pluses making 2 aluminum 3 plus and 3 nickels. All right, if you look at this table on our right there, one of the reactions you will find listed as a reduction, but one of them you'll only see listed, you won't see it as an oxidation, you'll also see it as a reduction. So anyway, this is kind of crazy, but let me find it here. Here's the nickel 2 plus going to nickel, and we want nickel 2 plus going to nickel, and that has a cell potential of minus 0.25 volts, and that part will be okay. But we also want aluminum going to aluminum 3 plus, and we don't have that reaction as is, but if you look right there, aluminum 3 plus is going to aluminum. It's the opposite of what we want. We want aluminum 3 plus as a product. It's giving us aluminum 3 plus as a reactant, etc., etc. So we're going to end up flipping the minus 1.66 into a positive 1.66. Because we don't want aluminum 3 plus as a reactant as listed in the table, we want aluminum 3 plus as a product. So if you flip the aluminum 3 plus reaction around, you get aluminum going to aluminum 3 plus 3 electrons, 1.66 volts positive. You can add that to the cell potential of minus 0.25 volts. 1.41 volts is the cell potential of this reaction. So that would be, I'd call it Michael's method, if you will, for calculating cell potentials. I make the half reactions look like our desired reaction in order to see what the cell potential it is. However, I do want to point out something else. In this reaction, it was 2 aluminums making 2 aluminum 3 pluses and 3 nickel 2 pluses going to 3 nickels. I didn't use 2 or 3 down there with the cell potentials. All right, so you do not multiply the E cell potentials by the numbers of electrons. It's the cell potential for any amount of chemical. We'll talk about where the numbers of electrons do make a difference here in a little bit, but for right now, just realize we are using those cell potentials as is. We don't multiply them by stoichiometries or anything like that, which feels kind of strange as a chemist, but that's how these things roll. And we will see later how those cell potentials can be affected by moles of electrons when we're talking about spontaneity, but not right now. If we wanted to calculate the E cell value, or E net, for the reaction between copper metal and silver plus, you can see first of all that copper metal is in the lower right, the southeast, and silver plus is in the northwest, the upper left. So we should end up with a positive value, but what is the value exactly? All right, well, silver plus an electron making silver, positive 0.80 volts, and copper 2 plus 2 electrons making copper, positive 0.337 volts. However, as you can probably see, we want copper metal as a reactant, not a product. We want the reaction between copper and silver plus, not silver plus and copper 2 plus or something like that. So you guessed it, we're going to flip the copper reaction. Copper going to copper 2 plus 2 electrons now will be negative 0.337. We're going to leave the silver reaction alone. We'll leave that as is. Cell potential 0.80 minus 0.337, positive 0.46 volts. That is the overall cell potential for this reaction. And if you balance it out, it's copper plus 2 silver plus, making 2 silvers, and copper 2 plus. So hopefully this has given you some experience about how you can make the cell potentials work for you. You need to flip an oxidized part around and then add them together to get the cell potentials. And all the positive cell potentials are spontaneous. They will work as written. You put those cells together and the electrons will start flowing. So this leads us to this kind of question. Let's say we have a cadmium 2 plus cell, and we have an iron 2 plus cell. And the question, which is quite legit, which reaction set is going to happen? All right. Will we have the first one, which is cadmium going to cadmium 2 plus and iron 2 plus going to iron? Or will we have the second one, cadmium 2 plus going to cadmium and iron going to iron 2 plus? Only one of those answers is going to work. And the question is, which one is going to work? An even better way is to say which one is spontaneous. In which combination will electrons start flowing by themselves? Which one will have something happen? So what we're going to do is we're going to use the cell potentials to combine them in order to give an overall positive E cell value. And that combination will tell us which of those possibilities is the correct or the spontaneous one. So in cell potential tables, you can look up these values. Iron 2 plus going to iron, minus 0.40 volts. Cadmium 2 plus going to cadmium, minus 0.44 volts. Now remember, we want the overall cell potential to be positive if it's going to be spontaneous, i.e. if it's going to happen when we put the cell potentials together. So as you can see right now, they're both listed as reductions, electrons are reactants. One of them has to be listed as an oxidation, where electrons are products. But if we flip, for example, the iron, you'd get a positive 0.40 volts and positive 0.40 0.0 plus negative 0.44 would still give you an overall cell potential which was negative. So that's not going to be spontaneous. However, if you flip the second reaction, you make cadmium going to cadmium 2 plus, now you're going to get a positive 0.44 volts when you flip it. And you add that to the negative 0.40 volts, positive 0.44 minus 0.40 still gives you the very small, however still positive 0.04 volts. So in order to get that value, we flip the cadmium reaction around. That means cadmium is a reactant and cadmium 2 plus will be a product. Likewise, iron 2 plus will be a reactant and iron will be a product. So this is the overall reaction that occurs spontaneously. That's the only combination of these two that gives a positive E cell value. And that's how you predict how things are going to work with these cell potentials. Here's another question. Can iodide reduce water? All right. And if you look at the table long enough, you'll see these two half reactions. The first one is water making H2 and hydroxide. The second one is iodide making iodine. Remember, iodide is I minus and iodine is I2. And if you combine them both together, the electrons cancel, and you've got a reaction where iodide and water are reacting to make iodine, hydroxide, and H2 gas. So that's the question. Is this reaction with iodide and water going to occur? Well, if you add the E cell values together, you can see, no, you're not going to get a positive E cell. This comes out to be negative 1.363 volts. And remember, positive voltages are the ones that are going to occur. So a negative voltage will not occur by itself. Negative cell potentials don't occur by themselves. They also imply that if you reverse everything, that reaction will occur. So if you take the desired reaction and you flip it, iodine and 2 hydroxide and hydrogen, making 2 iodide and 2 waters, you're going to get a positive 1.363 volts. That reaction will happen spontaneously. So iodide and water will not react under normal conditions. However, the reverse reaction with a positive 1.363 volts absolutely will occur. So you put iodine in with some base hydroxide and some hydrogen gas. Oh yeah, that's going to make iodide and water. So because the initial number though was negative, that means iodide does not reduce water spontaneously. So here's a similar question. It says, will mercury liquid reduce tin 2 plus to tin metal? Okay, so what we want to have here is we want mercury as a liquid to be a reactant, we want tin 2 plus to be a reactant, and we want tin metal, tin solid, to be a product. Well, if you look at this those two half reactions that are given, the first one is fine. All right, we've got tin 2 plus as a reactant, and we want to make tin metal, so that's half of the battle right there. But we also, though, want mercury as a reactant. And the cell potential right now has mercury as a product. So in order to answer this question, we need to flip that reaction around. We want the 2 mercury liquid to be reactant and the Hg2 2 plus ion and 2 electrons to be products. And when you flip a reaction, you change the sign. So positive 0.79 volts will become a minus 0.79 volts. So when you add the minus 0.79 volts to minus 0.14 volts, you get a very negative minus 0.93 volts, and negative E cell values will not occur by themselves. So we would not predict that mercury liquid would reduce tin 2 plus to tin. Its cell potential is negative. We need a positive E cell potential to make that happen. But let's go back to the iodine and water example one more time. Let's say we really, really want this reaction to occur, and it's got a minus 1.363 volts. But if you really, really want it to occur, this is kind of like taking the water from the bottom of the waterfall and transporting it to the top. You can figure out a pulley system. You can put the water over your back and hike or whatever you have to do. But I mean, it is possible. It's maybe not easy, but it's possible. And something like that can occur in electrochemistry as well. Non-spontaneous, i.e. the negative E cell values, can be forced to occur if you apply voltage from another source. So if you apply, for example, in this case, positive 1.363 volts, you can actually make iodide and water react. It allows this barrier to be overcome. And the voltage could be from another battery. It could be from, say, hydroelectric power, which is what we use in the Northwest, if you plugged it into an outlet or something like that. There's lots of ways that you can make the non-spontaneous reactions happen, but you do have to apply voltage from another source. Another spontaneous reaction is going to make your non-spontaneous reaction occur, which is kind of crazy. So in this case, we would apply 1.363 volts. This is an example of an electrolytic cell. It's a cell that doesn't happen naturally, spontaneously, but you can make it happen if you apply electricity, and this is the process of electrolysis. Electrolysis is more than just having your body hairs taken off, which is what sometimes people do when they want to have their body hair removed. They use electrolysis. This is the chemical version of that. You can make non-spontaneous reactions occur by applying this external electricity to it, which is pretty cool. And at one level, it might feel like you're cheating thermodynamics, but you're not, all right? You're actually making this happen by adding a spontaneous source of energy to a non-spontaneous reaction. It's pretty clever. And again, this is how all the aluminum metal is made. A lot of the chemicals we use in the lab are made this way. Very powerful process.